Check it out now, y'all.
nanoHUB-U, online instruction.
Hello again. Welcome to the last lecture in part one of this course called Fundamentals of Atomic Force Microscopy. In this particular lecture, I thought I'd run through some of the image artifacts that can creep into interpretation of AFM images, and just provide a general discussion of issues that possibly you might take into consideration as you work through some of the problems that you've been assigned or are interested in doing research on. I think the main problem with atomic force microscopy is that in principle everything works very well. There's very nice theories worked out to describe what's actually going on, but in practice you never really know what the shape of the tip is when it interacts with the substrate. And this lack of knowledge often causes misinterpretation of experimental data. So it's not only that the data you get is bad, but the data that you get is misinterpreted because you're assuming perhaps the best of all possible cases, when in fact your tip has been contaminated or your tip has actually been blunted by improper use of the instrument. So that's sort of the central theme of this lecture, is just things you have to worry about, maybe you need to work through occasionally just to provide sanity checks that you're in fact obtaining good data, good information, and that you're not over-interpreting the results that you obtain. I would encourage everybody to occasionally take SEM photos of your tips, both before and after you use them. You can learn an awful lot from these images, and I just show a few examples of some good tips. One is a tip that we imaged in the very early days when we were doing AFM here at Purdue. It's sort of the standard good tip image that we use in our lab. If you read the literature, you can find different techniques and procedures for producing extremely sharp AFM tips. If you have the availability of, let's say, a TEM, a transmission electron microscope, it's certainly worthwhile to try to image the tips that you're using both before and after you use them. Real tips tend not to be as sharp as the ones that I shown in the previous slide. Real tips get blunted quite easily, especially if the feedback parameters are set in properly. The tips tend to be broken. They have wedges, small wedged sections broken off from them. And of course, whenever a tip is damaged in this way, the images that you get are going to degrade markedly and will give you false information. There's a number of tip imaging artifacts that you should be aware of. These are pretty widely discussed in the literature, and they're broadly appreciated today, although in the early days of AFM, these things were discovered on the go as you took images. The double tip is a problem when the tip is actually fractured. There's occasionally a tip which has two sharp features in it, and those two sharp features then allow each feature in the substrate to be imaged twice. The tip dilation effect, we've discussed that in these VEDA simulations in the previous two lectures. The tip dilation will always cause a feature in the substrate to be wider than it appears, than it actually is. Oftentimes, if you're imaging a substrate that has very sharp feature in it, so for instance, if you're imaging, a nanometer size cluster, often the the cluster on the substrate will image the tip shape, right? So the sharp feature in the substrate produces an image of the tip rather than the tip producing an image of the substrate. This is, again, an example of a tip dilation effect. And then lastly, if the tip is wide and you're trying to study a feature that's depressed, the depth of that feature could be completely wrong, simply because the tip does not have enough space to fit into and image properly the region between the two features on the substrate. The double tip image is perhaps the easiest artifact to spot. When you have a double tip, you'll tend to get images which reproduce a curious geometric feature everywhere across the substrate. So whenever you see a feature reproduced at random positions across the substrate, that's probably a strong indication that your tip has been fractured and blunted, and your tip is producing the double image. So that's something to look out for. The tip dilation, in principle, the radius of the tip can be dilated or can be removed from the image. There are various algorithms that can be implemented to allow this to occur. In this particular slide, I just walked through a simple one simple algorithm that allows you to understand how the finite width of the tip actually causes the image of the substrate to be grossly broadened. In this particular algorithm, what you in principle do is you invert the tip, whatever the shape of the tip is, you invert that below the substrate. So the image is divided into an above and a below substrate regime. And so if you just watch this sequence of animations as your tip scans across the substrate, what you effectively do is you invert the shape of the tip and position it directly underneath the position of the tip on the substrate. When the tip encounters, let's say, a sharp feature, the tip is inverted at that sharp feature, right? And after the scan is complete, you then the image that you obtain is then obtained by tracing out the inverted tip in the above substrate regime. So in this particular case, that sharp blue feature imaged by this rather blunt triangular shaped tip would produce an image that I've got drawn in the red curve here. So this is the one tip dilation algorithm, and sometimes it's implemented in a software that you may be using. And if you really need to know the exact geometry of your substrate features, you'll have to go through this tip dilation approach. Sort of a poor man's version of this tip dilation is demonstrated in this slide. In this slide, I've got a sharp feature, a small, in this case, it's a small rectangular sphere, radius R sphere. That is imaged by a tip, which has a circular end form. The radius of the tip is R tip. And I just asked the question, what's the effective width of the feature on the substrate? And the effective width of that feature, the apparent width, is given by this parameter 2x. And just by doing some very simple geometry, you can show that the apparent width 2x is related to the radius of the tip and the radius of the feature. So sometimes it's very easy to correct the measured width of a feature using this particular algorithm, especially if you know the radius of the tip, right? You can solve that last equation here and work back and get a better estimate for the true radius of the feature, provided you know the radius of the tip. So you measure 2x, you measure our tip independently, and then you can work back and estimate the feature radius. I think when you're performing AFM scans, it's important to give some thought to the tip that you select, the cantilever that you select. Part one of this course, we focused mostly on contact mode AFM. Typical values for the cantilevers used in contact mode AFM are given in this slide. Typically, the spring constants are small, on the order of a half newtons per meter or less. When you move into the dynamic AFM, there's a much wider variety of cantilevers and tips that you can choose from. And of course, that's one reason why part two of this course has been designed. You'll go into the criteria for selecting a cantilever in dynamic mode AFM. It's a little bit more complicated than in contact mode AFM. I'd also like to mention that sometimes special tips are required for special jobs. And we've spent some time talking in the previous two lectures about the distortion in the AFM images that are obtained when you're trying to, for instance, image a trench that's been etched into a substrate. Sometimes a better way to go is to design a tip which is specifically tailored for the particular application. So in this particular example, the cartoon shows a boot-shaped tip, which allows you, for instance, to measure the width of a feature more accurately than if the tip has a radius of curvature associated with it. These special tips often have to be designed by the researcher for the particular application. So sometimes you can find a vendor that makes them, but very often you have to fabricate them yourselves. I'm often asked about tip care, what a student can do to optimize the performance of an AFM by properly taking care of the tip. And I think it's more an issue about being aware of what can happen to the tip. Tip can certainly become contaminated, even though you try not to contaminate it. It'll pick up stuff from substrates, especially if your substrates are dirty. These tips are very good at picking up loose particulates and acquiring thin organic layers, which degrade the performance of the tip in a particular application. So there are different techniques that have been tried to clean tips. These techniques are generally divided into a dry cleaning technique and a wet cleaning technique. Clearly, the wet cleaning technique uses a solvent, a chemical etching process. The dry cleaning techniques tend to remove the contamination of the tip by using energetic particle radiation, so you can use ozone cleaning techniques, argon sputtering, sometimes just indenting the tip into a soft substrate will effectively remove particulates that have accumulated on the tip surface. The tip surface itself is, of course, an interesting and a largely unknown parameter in atomic force microscopy. There are clearly oxide layers that form on silicon tips. The situation gets a little bit more complicated if you try to coat metals on the tips. So you often find gold-coated or platinum-coated tips that are used in conducting AFM applications. The microstructure of those gold and platinum coatings can wreak havoc on your images. And I just illustrate that in the next slide where I compare the microstructure of metal coatings for a tip that's been gold-coated using a thermal evaporation technique and a tip that has a gold-palladium coat that's been sputtered onto the tip. In the case of the thermal evaporation, it's much easier to it's much easier to perform this deposition technique, but the downfall is the apex of the tip is going to be coated with spherical blobs of gold, and it's very granular. It's often a very granular coating because you put such a thin layer of gold onto the tip. On the other hand, the gold palladium sputter-coated tips produce a much finer deposition. They're also metallic, and they're clearly advantages for that type of a coating. Students, especially when they're beginning to do AFM, don't have a sense of when the tip becomes dirty or when it becomes blunted. I just make 3 points here on this particular slide. How do you know when the tip is dirty? Well, one thing that'll happen is the resolution of your AFM images will change for the worse. So if you have a very clean tip, features in your substrate will be imaged with some sharpness. You'll be able to see different features. As the tip becomes contaminated or blunted, the sharpness of those features will certainly degrade. And so that's something that if you just watch for when you're taking data, if you're aware of that, you get a sense that the tip, it's time to insert a new tip. Another thing that happens is the adhesive force of the tip from the substrate will increase dramatically if it becomes contaminated with particulates or organic matter. So here I refer back to the lecture we gave on capillary necks, and the adhesive force produced by capillary necks on AFM tip substrate interactions. We derived a simple formula in week 3, lecture 1, and the simple formula says that the capillary force between the tip and the substrate is roughly 3 to 4 times what it would be if you measured the same liftoff force, let's say in a dry environment. So it's important for you to have a sense of what that liftoff force is, and if, for instance, that liftoff force increases dramatically from the value predicted from this simple approach, that's an indication that the tip's been contaminated with something, and perhaps it's time to change it out. The third feature that indicates a contaminated tip is just a cantilever deflection versus Z curve. So this is, you just approach the cantilever to the tip, you approach the tip to the substrate, and you retract. If there's a large hysteresis in that force, that approach retrace curve, that's an indication that the tip is no longer in good shape. So this requires you to do an experiment initially when the tip is new, and then if you become convinced or suspicious that the tip is no longer performing accurately, you reproduce that force versus distance curve. If you see a big hysteresis in that, that's probably an indication the tip's picked up some spurious material. Over the years, we've developed a variety of tests for scanning artifacts, and these are often routine procedures for the students that work in my lab. It's referred to as the R²C³ rule. It basically means you have to repeat the scan. Does the scan look the same as it did the initial time? If you reverse the scan direction, is your forward and backward images, how do they compare? Oftentimes we rotate the scan direction. This is very easy to do. In principle, the images on the rotated scan should be predictable. You should be able to predict based on an initial scan what the image should look like once the scan direction is rotated. So that's something to watch out for. We often encourage students to change the scan size. And in the process of changing the scan size, the important thing is to check, do the features scale properly? If they don't, then something's clearly wrong. So that's something that we often check. And then lastly, we're changing the scan speed through the important features that you're trying to measure. Are they independent of scan speed? This implies that you also have to readjust the proportional and integral gains. So when you change the scan speed by, let's say, a factor of 2, very often the proportional and integral gains have to change to, again, optimize the feedback. And if you get roughly the same image that you got the previous time, that's a pretty good indication that the instrument's at least performing as well as it can be. I will mention that to implement a lot of these checks, it's really important that your AFM software be able to subtract 2 images. Because you take an image, let's say, in the forward direction, and then you take another image in the retrace or in the backward direction. You look at the 2 images, just looking at the 2 images, they always bear a resemblance one to another. What you have to do is you have to physically subtract the 2 images one from another, look at the difference image, and that's where you're going to start to see systematic deviations, and that'll help you to interpret whether the tip is performing as you might expect it to. There's often questions about the care and handling of tips and cantilevers. I think every lab has developed a procedure that students are encouraged to follow. I just provide a list here of tip cantilever recommendations that we've developed over the years in our scanning probe lab here at Purdue. We really don't like to store these tips in plastic containers. We don't like to clean the tips in plastic beakers. There's all kinds of things that can go wrong with that approach. So as soon as we get tips or a set of cantilevers, we remove them from the plastic that they're shipped in. We tend to store them in quartz beakers, Teflon beakers. The beakers are then covered up and stored, labeled and stored in a way. We use fine tools in the handling of these cantilever chips. And these tools are dedicated to each student, so one student has control of their own tools. They're not commonly shared. This way you have some ability to control how clean they are, and students maintain the tools on their own. They're not a common use facility. We make use of this ozone cleaning and glow discharge a lot. It seems to help tips and clean off cantilevers, especially if they've been laying around for a long time. And some of my students have found it very useful to, after cleaning a cantilever, to store that cantilever in a clean solvent until it's actually used. So they'll actually drop the cantilever chip into a small test tube that's filled up with a solvent of their particular liking, and it seems to maintain the cleanliness of the cantilever oftentimes better than if the cantilever is just stored under ambient conditions. And so then lastly, the rule of thumb we always follow is, when in doubt, throw it out. We don't want to spend a lot of time trying to analyze data that may be taken with a contaminated tip or with a broken tip. So if there's any doubt about it, just start over again, get a new tip, because the worst thing that can happen is you'll have some data, and 2 or 3 months after the data's been acquired, you'll forget about the state of the tip, and you'll sit there and spend hours of your life trying to understand data that perhaps is not worthwhile understanding. So that's one of the rules we encourage new students to follow as a common protocol in the lab. So I think this basically concludes part 1 of this course called Fundamentals of Atomic Force Microscopy. We hope your experience in viewing these lectures has been rewarding. There is a feedback mechanism that's posted on the course webpage, and we welcome any input you have on how to improve the course. And we hope you take advantage of that. Let us know what we did right and what we need to improve on. Lastly, I'd like to emphasize that part 2 of this course, which is going to focus on dynamic AFM, that's going to start in about 2 weeks from today. The dynamic part of the AFM course is going to cover many of the techniques that we haven't had time to cover in the first part of the course. So I've focused mostly on the fundamentals of tip surface interactions and on the static cantilever approach to AFM. Dynamic AFM, of course, requires you to vibrate the cantilever at a resonant frequency, requires you to understand a lot more about the dynamics of atomic force microscopy. And then if you're registered for part 2 of the course, you're going to cover a lot of the topics that are indicated or that are shaded light blue in this particular slide. So we look forward to seeing you in part 2. I know Arvind Raman has been working very hard on those lectures, and they'll be quite interesting and quite insightful. So thanks for your attention throughout the past 5 weeks, and we'll see you in 2 weeks for part 2 of this course.